Something came from beyond the stars. Not in a science fiction movie, not in someone's imagination, but right here, right now, in our solar system. And what NASA just revealed about it 3 days ago is forcing scientists to question everything they thought they knew about visitors from interstellar space. Today, I'm going to show you the closest images ever captured of an object that was born in another star system. Images that were impossible to obtain until now. I'll take you through the unprecedented scientific operation that tracked this mysterious traveler across hundreds of millions of miles. We'll dive into the controversy that has astronomers and physicists debating whether we're seeing something truly natural or something else entirely. And I'll reveal what's coming on December 19th that could give you, personally, a chance to witness this cosmic anomaly with your own eyes. This is the story of 3I Atlas, the interstellar comet that refuses to behave like anything we've ever seen before. On November 19th, 2025, NASA held an emergency press conference. Not routine, not scheduled months in advance. Emergency. The topic: images of 3I Atlas captured during its closest approach to the Sun, a moment when the comet was supposed to reveal its true nature. But here's the problem. Earth was on the wrong side of the Sun. We were blind. Unable to see the most critical phase of this interstellar visitor's journey through our cosmic neighborhood. Or so we thought. What NASA revealed during that press conference was something unprecedented in the history of space exploration. While Earth was indeed blocked, humanity had eyes everywhere else. Spacecraft that were never designed to study comets suddenly became the most important observatories in the solar system. From Mars' orbit to the asteroid belt, from solar observatories to rovers on the Martian surface, a coordinated armada of technological marvels turned their instruments toward this single target. The images they captured are unlike anything in our archives. The data they collected is rewriting our understanding of interstellar objects. And the questions they've raised? Those are keeping scientists awake at night. But before we dive into what these missions discovered, before we explore the heated debate about what 3I Atlas really is, we need to understand why this object has caused such an extraordinary reaction in the scientific community. Because this isn't just another comet. This is only the third object ever confirmed to have entered our solar system from interstellar space. The third visitor from the vast darkness between the stars. And unlike the previous two, this one decided to put on a show. Let me take you back to July 1st, 2025, a routine night at the Atlas Observatory, the Asteroid Terrestrial Impact Last Alert System. Atlas exists for one purpose: to scan the sky and find objects that might threaten Earth. Night after night, its automated telescopes photograph the heavens. Computers analyze the images, flagging anything that moves against the background of stars. On that July night, the system detected something moving, something new. The preliminary orbit calculations immediately triggered alerts. This wasn't an asteroid from our solar system's main belt. This wasn't a known comet returning on a predictable path. The trajectory was wrong. Completely wrong. The orbit was hyperbolic, meaning this object was moving too fast to be gravitationally bound to our sun. It was just passing through. The astronomical community erupted. Within days, observatories around the world were tracking this newcomer. The International Astronomical Union's Minor Planet Center began collecting observations. And slowly, the reality crystallized. We were watching our third confirmed interstellar object entering our solar system. The first was Oumuamua in 2017, that bizarre cigar-shaped object that tumbled through our system and sparked years of debate about whether it could be artificial. The second was Comet 2I Borisov in 2019, which behaved more like a traditional comet, but still carried chemistry from another star system. Now, in 2025, we had 3I Atlas. But even from those early observations, astronomers noticed something strange. This comet wasn't behaving like Borisov. It wasn't behaving like any comet in our databases. Its properties were a mixture of characteristics that shouldn't exist together. Too large, too active, producing a coma and tail in ways that didn't match our models. The mystery deepened with every observation. And then came the realization that would define the entire scientific campaign. 3i Atlas would reach Perihelion, its closest point to the Sun, on October 29, 2025. Perihelion is crucial. It's when a comet's ices vaporize most violently, when the tail reaches its maximum glory, when we learn what a comet is truly made of. Miss Perihelion, and you miss everything. There was just one problem. On October 29th, Earth would be on the opposite side of the Sun from the comet. Geometry was against us. Our planet, with all its powerful telescopes, would be blind at the exact moment we needed to see. If you're enjoying this deep dive into one of the most significant astronomical events of the decade, hit that subscribe button. This channel brings you the latest cosmic discoveries, the real science behind the headlines, and the mysteries that mainstream media won't fully explore. And turn on notifications, because what's coming in the next few weeks with this comet might require emergency updates. Now, here's where this story transforms from disappointing to absolutely extraordinary. Because while Earth was blocked, Mars was perfectly positioned. Mars, our neighboring world, orbiting the Sun in just the right location to have a front row seat to 3i Atlas at Perihelion. And we don't just have telescopes on Mars. We have an entire fleet of spacecraft. Orbiters with cameras designed to photograph the Martian surface. A helicopter that proved flight on another world. Rovers with scientific instruments that can analyze atmospheres. What happened next was a testament to human ingenuity and the incredible foresight of having multiple missions throughout the solar system. NASA didn't just accept that Earth would miss Perihelion. They turned every available spacecraft, every mission with a camera or spectrometer, toward the comet. They coordinated an observation campaign unlike anything attempted before. And on November 19th, they revealed what they found. The closest image came from the Mars Reconnaissance Orbiter. MRO, as it's known, is a workhorse spacecraft that has been photographing Mars since 2006. Its high-resolution imaging science experiment camera can see details on Mars as small as a desk. But on October 2nd, 2025, MRO turned that camera away from Mars and toward the approaching comet. The distance? 19 million miles. Just 19 million miles between a spacecraft and an interstellar visitor. In cosmic terms, that's nothing. That's practically touching. An MRO captured it. An optical wavelength image showing the comet's nucleus wrapped in its cocoon of dust and gas. But wait until you hear what happened next, because MRO was just the beginning. Imagine this. A comet from another star system, traveling through the darkness for potentially millions of years, finally enters our solar system. It's October 2025. The comet is approaching its moment of truth, its closest pass by our sun, and waiting for it, positioned throughout space like pieces on a cosmic chessboard, are spacecraft built by human hands. Spacecraft that were designed for completely different missions, now united with a single purpose. Don't let this visitor escape without revealing its secrets. The Mars Reconnaissance Orbiter gave us visible light images, but MAVEN, the Mars Atmosphere and Volatile Evolution mission, had different eyes. MAVEN orbits Mars to study how the red planet lost its atmosphere over billions of years. Its ultraviolet spectrograph is designed to see things invisible to human eyes, to detect the signature of hydrogen and other elements as they escape into space. On September 28, 2025, MAVEN turned its ultraviolet instruments toward 3i Atlas, and what it captured was breathtaking. The comet's hydrogen envelope, the cloud of the lightest element in the universe, being blown off the comet by solar radiation, glowing in ultraviolet wavelengths. The tail, invisible to ordinary cameras, stretched across Maven's field of view like a ghostly river. This wasn't just a pretty picture. Ultraviolet observations reveal composition. They tell us what the comet is made of, what's evaporating from its surface, what chemistry it carried from its birth star system. Maven's data showed hydrogen behavior consistent with water ice sublimating from the nucleus. Water, the foundation of life as we know it, being shed by an object born light years away. But here's where it gets even more remarkable. While MRO and Maven watched from orbit, NASA had assets on the Martian surface. The Perseverance rover, currently exploring Jezero Crater and searching for signs of ancient microbial life, has cameras, really good cameras. Cameras that have photographed the Martian landscape in stunning detail, captured images of the Ingenuity helicopter, documented rocks that might contain biosignatures from billions of years ago. And on multiple dates in October, Perseverance looked up. From the surface of another planet, a machine built by humans photographed an interstellar comet passing overhead. Think about that for a moment. We have pictures of an object from beyond our solar system, taken from the surface of Mars. This is not science fiction. This is what we've achieved. The images from Perseverance show the comet as a bright point of light against the Martian sky, its tail extending away from the sun. The rover's cameras aren't designed for astronomy. They're built to study rocks and soil, but they were good enough to capture this historic moment. It's one thing to see a comet from Earth. It's another to see an interstellar comet from Mars. 3 missions at Mars. 3 different perspectives. 3 different sets of instruments: optical, ultraviolet, and ground-based observations. But NASA wasn't done. Throughout the inner solar system, spacecraft designed to study the sun had been tracking 3I Atlas for months. These solar observatories exist in special orbits that let them watch our star constantly, monitoring solar flares, coronal mass ejections, the solar wind that blows through space. But comets that pass close to the sun often enter their fields of view. And when an interstellar comet makes the journey, these missions don't just watch, they study it intensely. Punch, the polarimeter to unify the corona and heliosphere, is one of NASA's newest solar missions. It launched to study how the sun's corona connects to the solar wind filling our solar system. Punch uses wide-field cameras that can see huge swaths of space around the sun. And when 3I Atlas passed through its view between October 27th and 30th, Punch captured something extraordinary. Animated sequences showing the comet moving against the background of stars and the solar wind. Frame by frame, you can see 3I Atlas traveling, its tail streaming behind it, the coma surrounding its nucleus fluctuating as solar radiation hammers it. Punch's observations weren't from 19 million miles like MRO. They were from much farther away, back near Earth's orbit. But the wide-field view gave context. It showed the comet in its environment, interacting with the sun's particle wind. Stereo, the Solar Terrestrial Relations Observatory, added its perspective. Stereo actually consists of 2 spacecraft that orbit the sun at different positions, giving us stereoscopic views of solar activity. Both stereo spacecraft captured 3I Atlas, providing yet another angle, another set of data. The comet appeared in their coronagraphs, instruments that block the sun's bright disk to reveal the fainter corona around it. And then there's SOHO, the Solar and Heliospheric Observatory. SOHO is a veteran. It launched in 1995, before some of you watching this were born, and it's been staring at the sun ever since. SOHO has discovered over 4,000 comets in its lifetime, most of them sun-grazing comets that vaporize as they plunge into our star. But SOHO had never seen anything like 3I Atlas, an interstellar visitor, bright enough to appear clearly in its instruments, passing through its field of view at Perihelion. The images from SOHO show the comet's tail extending millions of miles, shaped by the pressure of sunlight and the solar wind. You can see the nucleus, that tiny solid core, and the enormous atmosphere it's producing as ice turns directly to gas in the vacuum of space. Now, if you're thinking this sounds like an unprecedented level of coordination, you're absolutely right. NASA's Science Mission Directorate, the division responsible for all these missions, made a decision. Every available asset that could observe 3I Atlas would observe it. This wasn't just about Mars missions or solar observatories. This was about using the entire infrastructure of spacecraft humanity has scattered through the solar system. Enter Lucy and Psyche. These are asteroid missions. Lucy is on its way to study the Trojan asteroids that shared Jupiter's orbit, ancient remnants from the solar system's formation. Psyche is heading to a metallic asteroid between Mars and Jupiter, a body that might be the exposed core of a failed planet. Neither mission is designed to study comets, but both spacecraft have cameras, and both were in positions where they could see 3I Atlas. Lucy captured its snapshot of the interstellar comet, adding one more data point, one more perspective. Psyche did the same. These observations might seem minor compared to the close-up views from Mars, but every observation matters. Every angle gives scientists another piece of the puzzle. Because here's the thing. We've never had this much data on an interstellar object. Never. Oumuamua flashed through our system so quickly, we barely got a good look at it. By the time we realized how important it was already leaving, fading into the distance. Comet 2I Borisov gave us more time, but it stayed far from Earth and Mars, and we didn't have as many missions positioned to study it. But 3I Atlas, the universe, gave us a gift. It came close to Mars right when we had multiple missions there. It passed through the inner solar system when our solar observatories were operating perfectly. It appeared in the fields of view of asteroid missions that happened to be in the right place, and NASA took full advantage. Tom Statler, NASA's lead scientist for solar system small bodies, said during the press conference that the scientific community is really excited about these new observations. That's an understatement. Astronomers are ecstatic. This is the data set they've been dreaming of since Oumuamua showed us that interstellar objects actually visit our solar system. But here's what NASA's Associate Administrator Amit Kshatriya said during that November 19th press conference, and I want you to listen carefully to his words, because they're important. He said, "I'd like to address the rumors. I think it's important that we talk about that. This object is a comet. It looks and behaves like a comet, and all evidence points to it being a comet. But this one came from outside the solar system, which makes it fascinating, exciting, and scientifically very important. Address the rumors. Why did NASA feel the need to explicitly state that 3I Atlas is a comet? What rumors was Kshatriya referring to? Well, that's where this story takes a turn into controversy, because not everyone is convinced that what we're seeing is purely natural. Some very serious scientists have been asking very serious questions. And the debate has been intense enough that NASA felt compelled to address it publicly. Before we dive into that controversy, if you haven't already, smash that like button. It helps this video reach more people who are curious about what's really happening in our solar system. And leave a comment. Do you think NASA is telling us everything they know about 3I Atlas? I read every comment, and I want to hear what you think. Now let's talk about the elephant in the room. The speculation, the theories, the possibility that some scientists are taking seriously enough to stake their reputations on. Let's talk about whether 3I Atlas might be more than just a comet. Professor Avi Loeb is not a fringe scientist. He's not a conspiracy theorist posting videos from his basement. He's the former chair of Harvard's astronomy department. He's published hundreds of peer-reviewed papers. He's advised NASA, served on prestigious scientific committees, and trained generations of astronomers. When Avi Loeb speaks, the scientific community listens, even when they disagree with him. especially when they disagree with him. And Loeb has questions about 3I Atlas. Serious questions. Questions he published in an article just after NASA's press conference, titled, "There is Nothing More Deceptive Than an Obvious Fact." That title alone should tell you something. Loeb is suggesting that what seems obvious, that 3I Atlas is simply a natural comet, might be deceptive. That we might be missing something. Let me be clear about what Loeb is arguing, because it's important not to misrepresent his position. He's not saying 3I Atlas is definitely artificial. He's not claiming it's an alien spacecraft. What he's doing is what scientists are supposed to do. He's questioning assumptions. He's pointing out anomalies. He's asking whether we're being rigorous enough in our analysis, or whether we're jumping to conclusions because those conclusions are comfortable. Loeb's central argument goes like this. When Oumuamua appeared in 2017, it exhibited characteristics that didn't fit the comet model. It had no visible coma, no tail, yet it was accelerating in a way that suggested something was pushing it. The standard explanation was outgassing, invisible jets of gas acting like tiny rocket engines. But the acceleration pattern was odd, too smooth, too consistent. And Oumuamua's shape, that elongated profile, was unlike any asteroid or comet we'd seen. Loeb proposed, controversially, that we should consider the possibility of an artificial origin, maybe a light sail, maybe debris from alien technology. The astronomical community largely rejected this idea, calling it speculative and unnecessary. Natural explanations, however unusual, were preferred over invoking extraterrestrial intelligence. Then came 2I Borisov, and it behaved exactly like a comet. Coma, tail, outgassing, composition matching what we'd expect from a natural object. The scientific consensus was, see, interstellar objects are just comets and asteroids. Oumuamua was probably a comet too, just an unusual one. Nothing to see here. Move along. But now we have 3I Atlas. And according to Loeb, 3I Atlas is exhibiting some of the same anomalies that made Oumuamua so puzzling. It looks like a comet in some ways, yes, but in other ways, it doesn't fit the pattern. And Loeb is asking, are we ignoring the inconsistencies because we want it to be a comet? Are we seeing what we expect to see, rather than what's actually there? What are these anomalies? Let's go through them, because this is where the story gets genuinely strange. First, there's the size and activity level. 3I Atlas is big. Estimates suggest a nucleus several kilometers across, and it's active, producing a massive coma and tail. But here's the thing. For an object that's been wandering interstellar space for potentially millions or billions of years, exposed to cosmic radiation and the cold of deep space, you'd expect the surface to be pretty dead. Volatile ices should have sublimated away long ago. The outer layers should be a radiation-processed crust that resists evaporation. Yet 3I Atlas became active while it was still very far from the sun, much farther than typical comets start outgassing. It's producing enormous amounts of gas and dust. Where is all this material coming from? How can an interstellar comet, ancient beyond measure, be this vigorous? Some astronomers have suggested that maybe it's a fresh comet, one that was ejected from its birth system relatively recently. But that raises its own questions. What mechanism could eject such a large comet on an interstellar trajectory? Second, there's the trajectory itself. 3I Atlas came into our solar system on a very specific path. It didn't just wander in from a random direction. Its orbit brought it close to Mars at almost exactly the right time for our Mars missions to observe it. It reached Perihelion when our solar observatories had the best view. The timing seems almost choreographed. Now, before you think I'm suggesting something outlandish, let me clarify. This could absolutely be coincidence. The universe doesn't care about NASA's mission schedules. Comets don't plan their arrivals. But Loeb points out that we should at least acknowledge when something seems statistically unlikely. And he asks, if you were an advanced civilization sending a probe to study a solar system, wouldn't you time its arrival to pass near planets where you could gather the most data? Third, and this is where it gets really interesting, there's the question of composition. The spectroscopic data from 3I Atlas shows water, carbon compounds, the usual cometary stuff. But there are also some unusual spectral lines, features that don't quite match standard comet models. These could be explained by unusual chemistry in its birth star system. Different stars produce different mixes of elements and compounds. A comet from another system should look different from ours. That's expected. But Loeb asks, how different is too different? At what point do we say, this isn't just unusual chemistry, this is something else? And he notes that we don't yet have the resolution to rule out artificial materials mixed in with natural ice and rock. We're looking at a fuzzy blob millions of miles away. We can analyze the light, but we can't see details. We can't examine the surface up close. We're making educated guesses based on limited data. Fourth, there's the morphology. The Hubble Space Telescope captured an image of 3I Atlas back in July, when it was still 277 million miles from Earth. That image shows a teardrop-shaped cocoon of dust around the nucleus. Teardrop-shaped, not the typical round or fan-shaped coma of most comets. The dust is distributed asymmetrically, which could indicate asymmetric outgassing, jets firing from specific points on the nucleus rather than uniform sublimation. Or it could indicate something else. Loeb suggests we should at least consider whether the shape might reflect an underlying structure. He's not saying it is artificial. He's saying we don't know, and we should be rigorous about ruling things out before we conclude it's natural. And then there's what happened after Perihelion. Ground-based observations from New Mexico on November 16th showed 3I Atlas with long streaming tails and a slightly green coma. The green color comes from diatomic carbon, C2, molecules created when carbon compounds break down in sunlight. That's normal for comets. Many comets show green comas. But the tail structure, multiple distinct tails visible in the photographs, is less common. Most comets have a dust tail and an ion tail, two components shaped differently by sunlight pressure and the solar wind. 3I Atlas appears to have more complex tail morphology. Again, this could be natural. Comets are chaotic systems, but it adds to the list of things that don't quite fit the simple model. Now, here's where NASA comes in. During the November 19th press conference, Amit Kshatriya explicitly addressed what he called the rumors. He stated clearly, this object is a comet. It looks and behaves like a comet. All evidence points to it being a comet. Notice the language. All evidence points to it being a comet. Not, it is definitely a comet. Not, we have ruled out all other possibilities. But evidence points to this conclusion. That's scientifically accurate language. That's a scientist being careful with words, but it also leaves room for interpretation. Kshatriya added that 3I Atlas came from outside the solar system, which makes it fascinating, exciting, and scientifically very important. On that point, everyone agrees. Whether it's a natural comet or something more unusual, this object is scientifically invaluable. We're learning about interstellar space, about planet formation in other star systems, about the materials and conditions that exist beyond our sun's influence. But why did NASA feel the need to address rumors at all? Press conferences about comets don't usually include statements reassuring the public that the comet is natural. The fact that Kshatriya brought it up suggests that the speculation had reached a level where NASA felt it was necessary to respond. And in the scientific community, that's noteworthy. Nikki Fox, Associate Administrator for NASA's Science Mission Directorate, emphasized during the conference that the comet was right inside the orbit of Mars, positioning it perfectly for observation. She focused on the scientific opportunity, the unprecedented data collection, the coordination of missions. But she didn't address the specific anomalies that Loeb and others have raised. She talked about what they observed, not about what those observations mean. Tom Statler, NASA's lead scientist for solar system small bodies, noted that the scientific community is really excited. He's right. They are excited. But excitement in science often comes from things that don't fit expectations. Anomalies drive discovery. If 3I Atlas were just a typical comet, yes, it would be interesting, because it's from interstellar space. But the level of excitement, the emergency press conference, the coordination of so many missions, all suggests this is more than just interesting. This is something significant. So where does that leave us? We have NASA saying it's a comet. We have Avi Loeb saying maybe. But let's be rigorous and not jump to conclusions. We have a set of observations that include both comet-like features and puzzling anomalies. And we have a public that's fascinated by the possibility, however remote, that we might be looking at something extraordinary. Here's my take, and I want to be clear about this. The default assumption should be that 3I Atlas is natural. Extraordinary claims require extraordinary evidence, and so far, we don't have evidence that demands an artificial explanation. Everything we've seen can be explained, with varying degrees of difficulty, by natural processes. But that doesn't mean we should stop asking questions. Loeb is right that science advances by challenging assumptions, by looking closely at anomalies, by not accepting the comfortable answer just because it's comfortable. The history of science is full of moments when the obvious explanation turned out to be wrong, when what everyone knew to be true was overturned by new data. Could 3I Atlas be hiding something we're not seeing? Could there be aspects of this object that don't fit the natural model as well as NASA suggests? Maybe. Probably not. But maybe. And in science, maybe is enough to justify careful investigation. The images released by NASA show a fuzzy comet with a tail. They show activity consistent with ice sublimating. They show spectral signatures matching cometary composition. All of that points to a natural object. But those images are from millions of miles away. We're not seeing surface details. We're not measuring with the precision we'd need to rule out every alternative hypothesis. And that brings us to the question that matters most. What happens next? Because there's an opportunity coming. An opportunity for observers on Earth to get their own data. An opportunity that might settle some of these questions, or raise new ones. December 19th, 2025. Mark that date. On that day, 3I Atlas will make its closest approach to Earth. It won't be dangerously close. We're talking about 170 million miles, but in astronomical terms, that's near enough for ground-based telescopes to get excellent observations. Professional observatories around the world are already scheduling time. Amateur astronomers with serious equipment are planning their imaging sessions. And for the first time since this interstellar visitor entered our solar system, Earth will have its turn. But before we get to what might happen in December, we need to understand what makes 3I Atlas so uniquely fascinating. Because even setting aside the controversy, even assuming it's completely natural, this comet is breaking records and defying expectations in ways that have scientists genuinely puzzled. Let's start with what we actually see when we look at this object. The Hubble Space Telescope image from July shows that teardrop-shaped cocoon of dust I mentioned earlier. Hubble is still the king of space telescopes for visible light imaging. Even with the James Webb Space Telescope now operational, Hubble's ability to capture sharp images of solar system objects remains unmatched for certain types of observations. When Hubble looked at 3I Atlas on July 21st, the comet was 277 million miles from Earth, At that distance, you might expect to see just a faint smudge, but Hubble revealed structure. That cocoon of dust coming off the solid, icy nucleus isn't symmetrical. It's teardrop-shaped, wider on one side, tapering to a point on the other. This tells us something important. The outgassing isn't uniform. Comets are lumpy, irregular objects. Their surfaces have different compositions in different areas. Some regions might be rich in water ice, others in carbon dioxide ice, others in more complex organic compounds. When sunlight heats the surface, these different ices sublimate at different rates, creating jets that fire from specific locations. These jets can actually change a comet's rotation and even slightly alter its orbit, like tiny rocket engines pushing the nucleus. But the pattern on 3I Atlas is unusual. Most comets, when they start outgassing, develop a relatively round coma as the gas and dust expand in all directions. Sure, you might see some asymmetry, but the teardrop shape Hubble captured suggests very directed outgassing. Strong jets from one hemisphere, weaker activity on the other. And remember, this image was taken when the comet was still pretty far from the sun. It was already actively producing this asymmetric dust cloud months before perihelion. Now fast forward to November 16th. Satoru Murata, an astrophotographer in New Mexico, captured an image that has been circulating through the astronomical community, and what his photograph shows is stunning. Long, luscious, streaming tails extending from the comet's nucleus. Multiple tail structures, clearly visible, stretching across the field of view, and a green coma, a distinctly green cloud surrounding the center. That green color is one of the most beautiful and scientifically informative features of comets. It comes from diatomic carbon, two carbon atoms bonded together, a molecule that forms when larger carbon compounds in the comet's ice break apart in sunlight. The molecule is unstable. It only lasts for a couple of days before breaking down further. But while it exists, it emits green light. Many comets show this green glow. But on 3I Atlas, it's particularly vivid. The tail structure in Murata's image is what really catches the eye. You can distinguish what appears to be at least two, possibly three separate tail components. The dust tail, pushed by sunlight pressure, curves gently. The ion tail, made of charged particles dragged by the solar wind's magnetic field, points more directly away from the sun. And there might be a third component, a sodium tail perhaps, which some comets develop. These multiple tails aren't unique to 3I Atlas, but they're not common either. Most comets show a simple two-tail structure, or the tails blend together so you can't easily distinguish them. The fact that we can see multiple distinct tails suggests high activity, lots of material being released, different types of particles and gases behaving differently in the sun's environment. Here's what's extraordinary. This is an interstellar object. It formed around a different star. The ice and rock that makes up 3I Atlas condensed from a protoplanetary disk that orbited a sun we can't even identify. It was born in a completely different chemical environment. The ratios of elements, the types of compounds, the isotopic signatures, everything could be different from solar system comets. And yet, it's producing a green coma. It's producing dust and ion tails. It's behaving in ways that are recognizable. This tells us something profound about the universe, the chemistry of planet formation, the processes that create comets. These are universal. Stars and their planetary systems, no matter where they are in the galaxy, follow the same physical laws, use the same elements, create the same types of objects. But within that universality, there are differences. And those differences are what scientists are desperate to measure. Because 3I Atlas is a sample of another star system. It's a piece of alien real estate that came to us. We didn't have to send a spacecraft on a century-long journey to another star. The other star sent us a sample. Think about what we can learn. The composition of the ice tells us about the chemistry of its birth nebula. The ratio of different isotopes, different versions of the same element, tells us about the nuclear processes in its parent star. The organic compounds, the carbon-based molecules, tell us about the potential for life in that distant system. Every spectrum we capture, every measurement we make, is data about a place we can never visit. And here's where the size becomes significant. 3I Atlas is big. Current estimates, based on its brightness and the amount of dust it's producing, suggest a nucleus several kilometers across. That's large for an interstellar object. Oumuamua was maybe a few hundred meters. Comet 2I Borisov was estimated at about 1 kilometer, but 3I Atlas might be 5, maybe 10 kilometers in diameter. We won't know exactly until we can resolve the nucleus directly, but all the signs point to a substantial object. A larger nucleus means more mass, more material, more complex geology. It means the interior could preserve pristine ice from its formation, shielded from cosmic radiation by the outer layers. It means when it outgasses, we're seeing material that has been frozen since this object's star system was young, potentially billions of years ago. We're seeing ancient chemistry, preserved in deep freeze, now being released as the sun's heat penetrates the surface. But it also raises that question I mentioned earlier. How did something this big get ejected from its birth system? Planets forming around a star can gravitationally scatter smaller objects. Jupiter has flung countless asteroids and comets out of our solar system. But there are limits. The bigger the object, the harder it is to eject. For a comet this size to reach escape velocity from its star system, something dramatic had to happen. Maybe a close encounter with a giant planet, a gravitational slingshot that accelerated it to interstellar speeds. Maybe a stellar encounter, another star passing through its system, disrupting orbits. Maybe its parent star went through a violent phase, a period of intense activity that destabilized the outer reaches of its planetary system. We don't know. We're guessing, and those guesses are based on models of how planetary systems evolve, models we're still refining. What we do know is that 3I Atlas is here, and it's giving us data we've never had before. The Mars observations at Perihelion, those close-up views when the comet was most active, captured it during the peak of its performance. MRO's image from 19 million miles shows the nucleus surrounded by that expanding cloud of dust. MAVEN's ultraviolet observations show the hydrogen envelope, the invisible component of the coma that extends much farther than the visible dust. And Perseverance, looking up from the Martian surface, saw it as a traveler from another world, photographing an even more distant traveler. There's something poetic about that. A robot on Mars, exploring a planet that might once have harbored life, pausing to photograph a comet from another star system. It's a moment that connects past, present, and future. Mars's ancient past, our present technological achievement, and the future question of whether we're alone in the universe. The Solar Observatory data adds temporal dimension. Punch, Stereo, and SOHO didn't capture single snapshots. They recorded sequences, time-lapse movies of the comet moving through their fields of view. And in those sequences, you can see the tail fluctuating. The brightness changes. The shape of the coma evolves. This is a dynamic system, constantly changing as solar radiation varies, as the comet rotates, as different regions of the nucleus face the sun. Scientists will spend years analyzing these observations. They'll model the dust production rates, calculate how much mass the comet is losing, estimate its lifetime. They'll study the spectral data, identifying molecules, measuring abundances, comparing to solar system comets. They'll analyze the tail dynamics, using the motion of dust particles to infer the comet's rotation and the strength of its outgassing. And they'll debate. Oh, will they debate? Because some of what they're seeing doesn't fit cleanly into existing models. The activity level is higher than expected. The onset of outgassing was earlier than predicted. The tail morphology is more complex than typical. These aren't necessarily signs of anything artificial, but they are signs that our models of comets, even interstellar comets, are incomplete. That's actually exciting. That's how science progresses. You make observations that don't match predictions. You refine your models. You make new predictions. You test them. And gradually, you build a better understanding of reality. 3i Atlas is forcing astronomers to think harder about comet physics, about interstellar objects, about the diversity of planetary systems. But the public, understandably, wants simpler answers. Is it a comet or is it something else? Is it natural or artificial? Black and white. Binary choices. And science doesn't always work that way. Science often lives in the gray areas, in the probably this, but we need more data space. And that's where we are with 3i Atlas. Probably a comet. Almost certainly natural. But unusual enough that we need more data to be completely sure. And fortunately, more data is coming. Because while the Mars missions and solar observatories had their turn, now it's Earth's turn. December 19th, when 3i Atlas makes its closest approach to our planet, will be our opportunity. Telescopes on every continent will track it. Professional astronomers will take spectra. Amateur astronomers will take images. The data will flood in. And maybe, just maybe, we'll find something in that data that surprises us. Or maybe we'll confirm that yes, it's a comet. Unusual, but natural. And we'll learn about its distant birth system. Either way, we win. Either way, we learn something new about the universe. So, what should you do? Well, if you have access to a telescope, if you're into astrophotography, December is your month. 3i Atlas will be visible, though you'll need a decent telescope to see it well. Check online resources for ephemeris data, predictions of where it will be in the sky. Point your telescope. Take your images. You might capture something scientists find useful. You'll definitely capture a piece of history. And whether you observe it yourself or just follow the news, pay attention. Because what happens in the next few weeks could be significant. We're watching an interstellar visitor, a piece of the galaxy beyond our sun's realm, and every day it reveals a little more about itself. Every observation adds to our understanding. Every spectrum, every image, every measurement is a piece of the cosmic puzzle. Before we move to what scientists are predicting for the December encounter, let me ask you, what do you think we'll find? Will 3i Atlas continue to behave like a comet? Will there be more surprises? Drop your predictions in the comments. And if you're enjoying this deep dive into one of the most significant astronomical events of the decade, make sure you're subscribed with notifications on, because I'll be covering the December observations as they happen. So let's talk about what's coming. December 19th is the date, but the observation campaign is already ramping up. Right now, as I'm recording this on November 20th, 3i Atlas is moving through space at tens of thousands of miles per hour, heading away from the sun, but approaching Earth's orbital path. Every night, it's getting slightly brighter from our perspective. Every night, astronomers are tracking it, updating their predictions, planning their observations. The geometry is favorable. Unlike at Perihelion, when Earth was on the wrong side of the sun, in December we'll have direct line of sight. No solar glare blocking the view. No awkward angles. Just a comet against the background of stars, moving slowly enough that long exposure photographs can capture exquisite detail. 170 million miles is still far. Don't misunderstand. You won't see this with the naked eye. You won't spot it with binoculars. But a good amateur telescope, 8 inches of aperture or larger, should be able to detect it. And professional observatories will see it beautifully. What will they be looking for? Several things. First and foremost, detailed spectroscopy. We need to break down the light from the comet into its component wavelengths and analyze what molecules are producing those specific colors. Every element, every molecule, has a unique spectral fingerprint. Hydrogen emits light at specific wavelengths. Carbon compounds each have their patterns. By studying the spectrum, we can identify what's in the comet's coma. We already know there's water. We know there's carbon, but the precise abundances matter. The ratio of different isotopes matters enormously. For example, the ratio of deuterium to normal hydrogen in water ice tells us about the temperature conditions when that ice formed. Different regions of a protoplanetary disk have different deuterium ratios. By measuring this in 3I Atlas, we can infer something about where in its birth system this comet formed. Similarly, the carbon isotope ratio, carbon-13 to carbon-12, varies depending on the chemical processes that created the organic molecules. The nitrogen isotope ratio has implications for the chemistry of the nebula. Every isotope ratio is a clue about conditions billions of years ago in a star system light years away. This is forensic astronomy. We're analyzing a crime scene, except the crime is just nature doing its thing, and the scene is another solar system. Second, astronomers will be monitoring the activity level. Is the comet still outgassing strongly? Is it weakening as it moves away from the sun? Are there variations in brightness that might indicate rotation, with more active regions rotating into and out of sunlight? Comets often show periodic brightness changes as they rotate. If we can detect that periodicity for 3I Atlas, we can calculate its rotation period. And from the rotation period and the pattern of activity, we can start to infer the shape of the nucleus. Is it spherical, elongated, potato-shaped like most small solar system bodies? Remember Oumuamua's odd shape, that elongated profile that sparked so much debate. If 3I Atlas also turns out to be unusually shaped, that would add another data point suggesting that interstellar objects might be systematically different from solar system objects. Or it might just mean we're seeing selection bias, that elongated objects are easier to detect because they reflect more light. Third, they'll be watching for fragmentation. Comets are fragile. They're held together by ice and weak gravity. Sometimes, as they heat up near the sun, the stress is too much. They crack. They break apart into multiple pieces. We've seen this happen with many comets. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before crashing into Jupiter. Comet Linear disintegrated in 2000, leaving a trail of debris. More recently, Comet Atlas, the solar system atlas, not the interstellar one, fragmented in 2020. If 3I Atlas fragments, that would be scientifically valuable, but also kind of sad. It would mean this traveler from another star system didn't survive its journey through ours. But it would also give us a chance to see inside the comet, to analyze the interior composition, which might differ from the surface. So far, there's no sign of fragmentation. The images show a coherent nucleus with a normal-looking coma. But stress fractures could already exist, invisible until they suddenly propagate and the comet splits. Fourth, and this is crucial, they'll be looking for anything anomalous. Any behavior that doesn't fit the comet model. Any spectral lines that can't be explained by known molecules. Any changes in trajectory that suggest non-gravitational forces beyond simple outgassing. This is where Avi Loeb's influence is felt. He's pushed the astronomical community to be more rigorous, to not just assume natural explanations, but to actively look for and rule out alternatives. Most astronomers still think the chances of 3I Atlas being anything but a natural comet are vanishingly small. But most is not all, and small is not zero. So they'll look. They'll measure carefully. They'll document everything. And if there is something unusual, something that genuinely can't be explained by comet physics, we'll know. Now, let's imagine for a moment, purely hypothetically, that something anomalous does show up. What would that look like? Well, it probably wouldn't be obvious. It wouldn't be the comet suddenly changing course and heading toward Earth. It wouldn't be radio signals or laser beams. If there were something artificial about 3i Atlas, it would likely be subtle. Maybe an unusual spectral line that suggests refined materials. Maybe variations in reflectivity that indicate surface structure inconsistent with a natural object. Maybe acceleration patterns that can't be fully explained by outgassing. These would be hints, not proof. And they would trigger intense debate and demand follow-up observations with more powerful instruments. The James Webb Space Telescope, for instance, could observe 3i Atlas. Webb's infrared capabilities could detect heat signatures, analyze the thermal properties of the nucleus, study the composition with unprecedented precision. So far, Webb hasn't been directed at this target, as far as public records show. But if something unusual appears in the December observations, you can bet there will be requests to point Webb at it. Same with ground-based radio telescopes. If there were any suspicion of artificial signals, radio observatories would be all over this. SETI, the search for extraterrestrial intelligence, would probably get involved. Though, to be clear, there's currently no indication that would be necessary. The comet is silent in radio wavelengths, as expected for a natural object. But here's the thing. Even if 3i Atlas is completely natural, even if every measurement confirms it's just an unusual comet and nothing more, the scientific value is immense. We're building a catalog of interstellar objects. We're learning about the diversity of planetary systems. We're testing our theories of planet formation against objects formed in completely different environments. Before Oumuamua, we had theories about how common interstellar objects should be. Those theories predicted we'd see maybe one per year if we watched carefully. And that prediction was roughly correct. We're seeing them. But the theories didn't predict the diversity. They didn't anticipate that each interstellar visitor would be so different from the others and from solar system objects. Oumuamua was weird in one set of ways. Borisov was normal, almost boring. 3i Atlas is weird in a different set of ways. What will 4i be like? What about 5i, 6i, and beyond? As our detection systems improve, as surveys like Atlas and Pan-STARRS and the upcoming Vera Rubin Observatory scan the sky more comprehensively, we'll find more, and each one will teach us something. The Vera Rubin Observatory, in particular, is going to revolutionize this field. When it becomes fully operational, it will survey the entire visible sky every few nights, going deeper and covering more area than any previous survey. It will find asteroids, comets, supernovae, distant galaxies, and yes, interstellar objects. Lots of interstellar objects. Predictions suggest Rubin could detect dozens per year. Imagine that. Dozens of interstellar visitors annually. We'll go from a situation where each one is a major event, press conferences and emergency observation campaigns, to a situation where they're routine. We'll have statistical samples. We'll be able to categorize them, study populations, understand what types of objects get ejected from planetary systems and why. But we're not there yet. Right now, in late 2025, 3i Atlas is special. It's the third. It's the one that gave us the best data. It's the one that came close enough to Mars for unprecedented observations. And it's the one that's causing genuine scientific debate about what we're seeing. The December observations will add enormously to our understanding. As the comet approaches Earth, the viewing angle will change. We'll see different faces of the nucleus as it rotates. The lighting will be different from what Mars missions saw at Perihelion. We'll get complementary data that, combined with the earlier observations, will let scientists build three-dimensional models of the comet's shape and activity. And then, after December 19th, 3i Atlas will continue its journey. It will move past Earth, heading back out toward the outer solar system. It will cross the orbit of Mars again, then Jupiter, then Saturn, Neptune, and eventually pass beyond Pluto's orbit. The sun's gravity will still be pulling on it, slowing it down, but not enough to capture it. 3i Atlas has escape velocity. It's leaving. In a few years, it will be too faint for even our best telescopes to detect. It will fade into the background of space, lost among the countless stars, and it will continue on its journey through the galaxy, perhaps for millions or billions of years, until maybe, just maybe, it encounters another star system. And if that star has planets, and if one of those planets has astronomers, they'll see an interstellar visitor entering their space, and they'll wonder where it came from, and they'll debate what it is. But we'll know, because we saw it. We photographed it. We analyzed it. We had our moment with 3i Atlas. And whether it's a completely natural comet or something with hints of mystery we couldn't quite resolve, it will remain one of the most significant astronomical observations of the 2020s. You know what's amazing? We live in a time when we can do this. We can detect objects from other star systems. We can mobilize spacecraft across the solar system to study them. We can coordinate international observation campaigns. We can have serious scientific debates about the nature of interstellar visitors. This is the future that science fiction promised, and we're living it. So stay tuned. Follow the news. Watch for updates on the December observations. This story isn't over. In fact, it's just reaching its climax. And whatever we learn in the coming weeks will shape our understanding of the cosmos for years to come. If you've stuck with me through this entire deep dive, thank you. This is complex stuff, and the fact that you're interested in the real science, the nuances, the debates, that's awesome. That's how we move forward as a species, by being curious, by asking questions, by not accepting simple answers to complex mysteries. Hit that like button if you found this valuable. Share it with anyone you know who's fascinated by space, by astronomy, by the big questions. And subscribe, because I'll be following 3i Atlas through December and beyond, bringing you updates as new data comes in, new papers get published, new discoveries get made. The universe sent us a visitor from the stars. Let's make sure we learn everything we can from it. Let's make sure we honor this opportunity, because opportunities like this don't come often. And when they do, they remind us that we're part of something much larger than ourselves. We're part of a galaxy full of star systems, full of worlds, full of comets and asteroids and planets, and who knows what else. 3i Atlas came from out there, from the vast darkness between stars. It entered our little corner of space, gave us a show, and soon it will leave. But the knowledge it leaves behind, the data, the insights, the questions it raises, those will stay with us. Those will push science forward. Those will inspire the next generation of astronomers to keep looking up, keep wondering, keep searching, because somewhere out there in the galaxy we call home are answers. Answers to questions about how planetary systems form, how common life might be, whether we're alone, what wonders exist beyond our current reach. And every so often, the universe sends us a clue. A piece of the puzzle. An interstellar traveler that tells us a little bit more about what's out there. This is one of those moments. This is 3i Atlas. And whatever it is, wherever it came from, it's magnificent. Thanks for watching, and clear skies.